Good morning, everyone. So let's continue the problem of the extension of the the estimation of linear regression models, and in particular for the case of the least square. And we saw that there is the need of a modification of this estimation error, which is called prediction error method, in order to include possible the presence of possible non-correlated noises. So the main idea with when considering the prediction error method is that we need to model also the noise, so the stochastic models. So it means that the outputs of the models are not deterministic. And in this case, as for the linear squared, you need to minimize the prediction errors. But the problem is now that prediction errors is a vector, is a stochastic process. And of course, the least square method is a special case of prediction error method. We will see later. And now the estimation error is described with this equation, where the epsilon, so the estimation error, is a function, of course, of t, and depends on the parameter vector theta, the unknowns. So normally is defined as with difference, so the real measurements with respect to the estimation of the output at the instant t, when using the measurements up to the instant t minus 1. So the estimator uses all the data up to the instant t minus 1. So t minus 1 is the most recent data that is used for providing the estimation of the vector y, or the scalar y, at the instant t. And as for the least square, so the linear regression models, we have this expression. And this methodology can be applied to a number of models that are different from, for example, the ARMAX models. So let's see which kind of classes. So for example, in order to find the optimal prediction, if you remember, optimal means that the estimation error is white. And for the first following system, we assume that the noise is white. And under this assumption, you can derive this estimation, which is a function, as is written here, of all the data available from theoretically in practice, in principle, from minus infinity to t minus 1. And there is a simple exercise you can also, using the definition, let's see if you are able to find the predictor for these three models, but it's not the topic of this lecture. So let's go to the problem of the prediction. So the prediction is described in general when we are considering the stochastic problem. A filter which provides a prediction of the output for a dynamic system, given all measurements output in. So the predictor is designed as follows. So define the model structure. Normally is more complicated than an ARMAX, for example. It can be, as you know from the lecture 1, can be an output error or an ARMAX or a Boxe-Jenkins. And then once you have selected the model structure, you need to use the predictor. So as we saw at the end of lecture 1, you see that you know that the predictor is a function which provides, which perform a processing of the input and the output in a suitable way. And normally is these two functions, or they can be considered as transfer functions, are constrained such that the predicted output depends on past data. And of course, the third point is to define a cost function that needs to be minimized. But for the case of linear regression models and least square. You know that the cost function was the common least sum of the squared errors. So the optimal prediction means that in the memoization that the predictor minimizes the variance of the prediction error. So we will consider the general structure. So is this structure slightly modified in order to have that the output of the model as the form. So you have the output of your system is given by a transfer function which describes the deterministic part and another, this transfer function h describes the stochastic part of your model. E is important because in general is a zero mean, can be zero mean, and as in this case, and as a particular can be correlated or not correlated depending on the form of this matrix, of the matrix gamma. And normally is assumed that the function, the transfer function g computed in 0 is equal to 0. So in order to find the optimal predictor, you need to solve this equation. So they need to find the minimum of this expression with respect, of course, now is not directly on the parameter, but is minimized depending on the estimation, on a given estimation, where the prediction error is described by this expression. And of course, the estimation is a function of the data from, in principle, from minus infinity to the instant t minus 1. So as a result, let's see that the let's assume that the output depends only on the past measurements. And another assumption that normally is valid is that because especially if the input is deterministic, U is deterministic and E is stochastic, so they are uncorrelated for t minus t lower than S, then the predictor you can obtain by replacing in this expression the replacing the value of the model and its prediction. So you come out with this expression which you can see here that you find the matrix H, which is, and the matrix G. So these represent the formulation of the optimal prediction. So if the optimal prediction is so the predictor, sorry, is optimal, it means that the prediction error, which is defined by these expressions, needs to be equal to E. So it means from the definition of we saw at the beginning that the estimation, the covariance matrix of the prediction error needs to be equal to the one of the error. The same solution can be found, so it's valid also. We will see something in when we are considering the not only input-output models but state space model. And in the case of state space models, we can replace the original model structure with this state space model when, well, the number of parameters is increasing because you have matrices F, B, C, and also you have the state X, where normally V and E are, you can see here that you have a process error and the output error. So you have these noises that are uncorrelated Y sequence with zero mean and covariance matrices R1 and R2. And for the case of the optimal filter, for the case of this of this state space model, you have the well-known solution of represented by a Kalman, the so-called Kalman filter. This is the topic that is normally addressed in another of our courses. How we can find the best model structure of for our predictor? So the best model is obtained by minimizing the prediction errors for all t. So again we have the criterion, which is represented by the cost function v of n, which is minimized under this expression. So it means again that you want to find the minimum with respect to the vector, the unknown parameter vectors, vector theta, of the cost function v of n. N is the number of data, and the argument is theta. And the v of n depends on the estimation error in a suitable method. So depending on the model structure, the prediction filter and the criterion function, the minimization is more or less difficult. So in general, the cost function is a function of, let's see, in general, h of Rn of theta, where h is a scalar valued monotonically increasing function, like, for example, remember, for example, the square, the square of a value, increasing, so the function square satisfies this solution. And R of n, capital R of n, is a sample covariance matrix of the prediction error. It has this form. So you can see here that the function is a scalar, but is the output h has the input r, which is a matrix. So it means that this function is a function that transforms from a matrix value to a scalar function. Well, in this case, for example, the h can be selected as the trace function or the determinant, because they are, you know that they are also monotonical increasing function. And for the case, as already remarked, for the case of single output, because the problem in this case you have multiple output, but for the case of a single output, the v of n is very simple because it comes out to be directly the summation of the square of the prediction error. So now how we can define the PEM, so prediction error method algorithm? So it can be defined once you have defined the following quantities, so the following term. The model structure, so it means that you need to select g of h. Remember from the first lecture, if when you select an ARMAX model, an ARMAX model, a Boxe-Jenkins, or an output error. The choice of the predictor, usually you select the optimal mean square predictor, and then the choice of the criterion function, which is a scalar value function for all the prediction error. Well, let's see two cases which concern, of course, the computational aspects. In the case, the first case when an analytical solution exists. So if the predictor is a linear function of the unknown parameters for the case of the previous least square method, so the function v of n is simple, so the solution can be found in closed form. So it means that an analytical solution exists. And this is the case as represented here. You can easily verify that for the case, in this case, so for the case of scalar function, the PEM is equivalent to the linear regression, so the least square method we saw in the previous module of this lecture too. And of course, this holds for finite impulse response or the ARX models, but not for ARMAX or output error model, because the structure is more complicated, because you know that in the ARMAX or especially in ARMAX or Boxe-Jenkins, you introduce a filtering also, not only with respect to the poles, so the regressive part, but also with respect to the error. So you are introducing some delays of the error, which makes the generation of your predictor more complicated. So this is the second case when no analytical solution exists. So it means that the prediction can depend non-linearly on the data, and in this case a numerical search algorithm is required in order to find the theta which minimizes the function. But normally in numerical minimization you have a nonlinear, the minimization of a nonlinear function, and in this case you can be trapped in local minima. Sometimes it's quite consuming because depending on the search algorithm, it depends on the number of steps required to converge to the solution, and it can be computational complex. And also we have a problem of universalization. So there are normally two standards, just a remark, we don't want to enter into the details, but we have two solutions for finding normally associated with the problem. The first is called the Newton-Raphson algorithm, where, well, the derivative of the cost function can be, this is the problem, it represents the problem of the algorithm, because as you can see here, it's very accurate, but and as it presents fast convergence, but it requires the computation of a second derivative of the cost function. On the other case, you have a Gauss, which is called Newton-Raphson. Gauss-Newton is computational less intensive algorithm, but with a lower rate of convergence, because it's actually using a filtering of the, so it doesn't require the computation of the second derivative, but it's using, if you want, if you enter in the implementation of the algorithm, as you can see here, is using actually some filtering of the output, so is more is less accurate, but and is lower, but can represent an alternative. And there are some also, as for this case, there are some gradient-based methods. So gradient-based means that you don't need to compute the second derivative, but they have a slower convergence rate. So in order to summarize this sketch of the method, so the PEM is a general method to obtain parametric model of a dynamic system. And the following choices define the prediction error method. So it is represented by a selection of a more complicated model structure, the choice of the predictor, and also the choice of the criterion function. Well, in principle, the PEM is able to minimize the prediction error given the model structure and the predictor. And we will not show here, but the prediction error method provides the solution that have interesting properties. In particular, they are consistent statistical efficient. So it means that they are quite accurate. So we need to include, to consider some approximations, because the PEM is useful for underparametrized models. So when underparametrized means that you are considering a model with a reduced number of parameters. And the model fitting can be controlled by pre-filtering the data. So because, as you remember in the first lecture, when you want to reduce the complexity of the model, perhaps you need to pre-filter your data in order to remove all the information you don't want to be included in your model. When the prediction errors depend linearly on the parameters vector, as for the case of the selection of ARMAX or FIR models, so the PEM estimates are obtained through linear regression, so it means that you have the same solution of the least square approach. When you are considering more complicated model structure, like when you are considering state space models or ARMAX, box adjacencies, or output error, so the search algorithm is more complicated, and because the predictor is nonlinear with respect to the parameters. So let's see the last part of this lecture, when we are considering an alternative, a modification of the least square method, in order to obtain, to maintain the same simple solution on one side of the least square, but also coping with, for example, correlated noise or a more complicated noise. So let's come back to the problem of the ARMAX model. So you remember that the ARMAX model has this structure, or equivalently it can be written as here. So the output is a parametric model of the inputs and also of the output, where NA is the number of delays of the output and NB is the number of delays in the input. Sometimes, note that sometimes NA is equal to NB in order to reduce the degrees of freedom. So you remember that the least square estimate leads to this solution, where when can be simplified in order to consider if you introduce the expected value of your solution. So when you consider the expected value, so here in particular, the expected value of your solution is equal to expected values of this matrix, which is no longer deterministic, and the expected value of this other matrix. Note that this expression, this computation is possible only when n tends to infinity. So consequently, the expected value of E is equal to 0, so it means that your estimate is consistent. This expression, so this, of course, this cannot be 0, so only this one can be 0. So it means that this expression, this one, needs to be 0. And if you remember, this expression can be verified when the error, the estimation error, is uncorrelated and that it is a white noise. And in this case, you have the least square estimate. In the case of colored noise or correlated noise, the estimate is not correlated. So this is a problem, because when the noise is correlated, so it's not white, the estimated values is not 0. Then we use, the alternative to this problem is to still use the least square method, because it's very simple, but the problem is that the solution provided is not consistent, of course. Use the prediction error model, the method. Of course, they are modeling the noise, but the problem is that they are generally can be used for general model structure. They have good properties of the estimate, but in some cases are computationally quite demanding. So the alternative to use an instrumental model variable method, well, the problem of the instrumental variable method is that they don't consider, as we will see later, the model of the noise. So it means that they, for example, provides the estimation of the deterministic part in very good with very good accuracy. And you must use, for example, a PEM method for finding the model of the noise. So it can be an alternative, but it requires a two-steps procedure because they provide consistent solutions for also correlated noise, but its problem is that they are less robust and statistically less effective. So let's see how we can design this solution. So the IV method requires to introduce a vector, because the principle, I come back here, the principle is that you must guarantee, so the idea of the instrumental variable method is that you replace your variable with the problem. The problem is due to the fact that you are using an output, this y, which is correlated. So you need to modify in some sense your matrix phi in order to have that is correlated with phi, of course, because these matrices need to be non-singular, but must be uncorrelated with phi, must be uncorrelated with epsilon. So the idea here, in order to close, is that you introduce, as you can see here, instead of y, the matrix, the variable, the vector or the variable y, you introduce is called the instrument z, which you can see here, that replace here the output y. And when you have replaced the instrument z, you have the same solution, but the same solution, as you can see here, you replace so y and then the phi with this instrument z. So z is usually called instrument. Note that when z is equal to phi, the IV estimate reduced to the LS estimate, which holds when you are considering, for example, ARX models or FIR models, but not since we are not considering this kind of models. LS is not, at least if you want to obtain consistent estimates, you cannot use the least square method. So let's go to the solution. How you can choose these instruments? Because of course it's very easy to say, okay, replace the phi with another sequence of measurements. Of course, they can be chosen, for example, in order to have some data that are or outputs that are uncorrelated with E, because remember that the consistency of the estimates is obtained if the instruments Z is uncorrelated with respect to the epsilon, and in such that the matrix Z, remember that Z replaces phi of t in the least square, so phi is replaced by V, should be uncorrelated, maximally correlated, because it has to have full rank. In other words, is essential that Z of t and phi of t are correlated. Very important, this note. In practice, these requirements are fulfilled by choosing the instrument to consist as, very simply, delayed or filtered inputs. So the inputs, as you can see here, the instruments are commonly chosen as such that Z is equal to, you can see here, you can include the inputs, because the input, you know, they are usually they are uncorrelated with respect to E, but they are already correlated with phi, and Eta is obtained by filtering the input in this way. So normally, as you can see here, a very simple choice of your instrument is to select a number of, you can see here, of this part is replaced again by the number of inputs. Of course, you cannot put the same input values as here, because it will be a singular metric. So you normally select ut minus 1 up to ut minus NA, and then ut minus NA minus 1 up to t minus NA minus NB. So you use an increased number of delayed inputs. Sorry. So in this case, U and Y, of course, are assumed to be independent. So this is the most common solution and the easier. Of course, you can, well, the estimation is not so good, but at least can be a starting point for finding your solution. And then, so in order to conclude this part, so the implementation, because the implementation of a PEM algorithm can be complex for a complex model structure. So in some cases, you can consider the solution provided by least square, but the problem of the least square is that is biased. So it means it's not consistent. So it means that expected value of your solution minus the expected value of the real is equal not to 0, but is B is the bias. So it's biased. This is the meaning. Instead of 0, if you remember me, is when all the assumptions of the least square are satisfied. But if they are not satisfied, so the solution is biased. There is a cure. So use a IV method, which uses the instruments. The instruments are correlated with the disturbance to make to provide a least square like solution, consistent. So in this case, is a solution are consistent, but the problem is that it can be shown that they can have a higher slightly variance than PEM estimate. So remember that we are considering IV method are simpler, but the accuracy cannot be so good as the PEM methods. Okay, thank you for your attention.